Hello, everybody. This is going to be lecture 4 of module 3, where we talk about the properties of OLS estimates. So the first thing we're going to talk about is OLS is going to solve equations 1.1 and 1.2 by construction. So for example, we have the sum of the error terms, the predicted error terms, is going to equal 0. So this is, again, just saying the expectation of the error term is going to equal 0. So that's what we saw a while ago in equation 1.1. 1.2 was the expectation of error given x, and we needed that to equal this, and if this equals 0, then this has to equal 0 as well. So by construction, this is going to happen. We kind of used the method of moments to ensure this would happen, and we designed our OLS model with this in mind. So also by construction, we're going to have the point x bar, y bar, meaning the averages of both of the variables, is always going to be on the regression line. And the second point is going to be when x equals 0, you're just going to have y is going to equal beta 0. So we're able to kind of construct these important things that we were looking for using that algorithm of either method of moments or the more calculus-based one I also showed you. So we're going to talk about the total, explained, and residual sum of squares. So for each observation, each I from 1 to n, we can write our equation of yi, the true y, the true sale price of the home, equals the predicted sale price of the home plus the error term, the predicted error term, the predicted epsilon for that observation. So we're going to define the total sum of squares, so SST, explain sum of squares, SSE, and residual sum of squares, SSR. So the sum of totals, so the sum of squares total, or the total sum of squares, is going to be yi minus y bar. So yi minus the average y squared. The explained sum of squares is, now we're just going to say, okay, instead of using the true value, we're going to use the predicted value. That's going to be minus the average squared. And the residual sum of squares is just going to be epsilon hat squared. So OLS is always going to yield, or by design is going to give us a total sum of squares is going to equal the explained sum of squares plus the residual sum of squares. And now we might be interested is, okay, well, of the total sum of squares, what percent did we explain? What percent was our model able to kind of help us out with? So we're going to use something called R squared, or a goodness of fit measure. So we're going to say, okay, well, how well did x explain y? So what we're going to do is we're going to take the sum of squared errors, and we're going to divide by the sum of total squares, or the total sum of squares. So what that's going to give us is, if our explained is 80% of our total, then we're going to say, okay, well, we explained 80% of the variation in the data. That's pretty good, right? We're able to explain 80%. That's some helpful criteria. Or what we can do is we can do 1 minus the sum of squared for the residuals divided by total, right? So we can either do it this way or this way because they're equivalent. If you add this value and this value, you'll get 1. So the R squared is going to be, the interpretation is the fraction or the percent of the sample variation in y that you can explain using x. So this is a helpful criteria in saying, okay, well, this is how good we fit the data using our OLS strategy. And R squared is always going to be in 0 and 1. You can just convert it. You can multiply by 100 and convert it to a percent if you prefer. And most statistical programs, if not all, will calculate R squared for you automatically. And we'll see that when we actually go to R and look at some of these regressions. So R squared gets its name from being the square of the sample correlation between yi and y hat squared, and y hat I. So in regressions, though, it's common to get a low R squared with cross-sectional data and a high R squared with time series data. Therefore, R squared is not a good measure, but it's one thing that you can look at. So rather than just picking one metric or one number to say, okay, this is how good my regression is, you have to take all of it into account. I will say R squared is helpful when you get a large one. It's exciting or something like this. But at the end of the day, most people don't really care about your R squared, rather about statistical inference, which we'll talk about in a little bit. But the R squared for this equation here, for that CEO salary and return on equity, was 0.01. So this equation only explained 1% of the variation. So that's quite low, but doesn't mean that the model is unhelpful or anything like that. So units of measurement. So this is kind of another important thing, because sometimes you want your coefficients to be directly interpretable. So for example, in this previous regression here, we were using thousands of dollars. So if I increase my ROE by 1, I think this is actually in thousands of dollars. If I increase this by 1, then, oh no, sorry, salary is in thousands of dollars. So if I increase my ROE by 1 unit, then this is going to increase by $18,000. But in here, rather, if I use dollars instead of thousands of dollars, if I increase my ROE by 1, I'll increase my salary by, again, $18,000. So the exact numbers are the same. It's just however you want to interpret that value. And that's important, because you want to be able to kind of make sure that you're making the right interpretation. The R squared is exactly the same. The sample size is exactly the same in both of these. So R squared does not care about your units of measurement. And then the same thing here is we instead measure return on equity as a decimal percent instead of a regular percent. So we were here where it was in percentages, so it was 0 to 100, but because we did it as a decimal percent, where we divided by 100, this is going to increase the coefficient by a factor of 100. So if whichever way you scale, the coefficient will react appropriately and will always be the same number. So however you scale your data to make an interpretation, it's up to you. So functional form. So I mentioned this before, but when we say linear, we mean the parameters are linear, not the data itself. So for example, beta 1 enters into the model linearly, meaning that beta 1 is just a coefficient multiplied by something. So it's not like log of x raised to beta 1. That would not be a linear model. So rather we can say, okay, well, I can do whatever I want to x. I can say beta 0 plus beta 1 times the log of x. I can make it regular x. Or here I've made it a quadratic. I can make it a constant term or an intercept term. And I can do plus x regular. And I can do a multivariable equation where I have now x squared. So again, we say this in classical linear regression. When the model is linear, we mean the parameters are linear. The parameters are just multiplying a variable. So logged variables. This is really common in economics, where we log variables because the interpretation is really nice. So the interpretation allows for percentage comparisons. So instead of saying a 1 unit increase in square footage, meaning 1 extra square foot of room in a house will cause this many dollars for a house sale, I can, if I log, so let's say I'm logging housing sales. If I log that, I can say a 1 unit increase in the 1 unit increase in square footage causes a percent change in the housing price. So that's a much different interpretation than saying a 1 unit increase in dollars leads to a 1 unit increase, or an X amount of or beta $1 increase. Rather, I can say a 1 unit increase in this leads to a beta 1% change in total packs or housing price or something like this. So interpreting the coefficient on logged variables, you don't have to know the math, but rather you do have to know how to interpret them. So if you have a level, which is just regular y and x, you interpret it as a 1 unit change in x leads to a beta 1 change in y. Now, if you log x but leave y the same, you say a 1% change in x leads to a beta 1 divided by 100 unit change in y. If you log y and leave x regular, you say a 1 unit change in beta 1 or in x leads to a beta 1% change in y. So use this table to help you with interpretation. There's also other resources online that kind of have examples. I'll try to find, I know of one good website. I can try to find it for you that kind of has an example like in English of each of these things. And it's really helpful to understand the interpretation. So here are some other notes on logs. We estimate elasticity a lot in economics. So pretty much a log-log model. If you end up wanting to do this, we can talk about this more, but you should read this slide and kind of think about it. But using a log transformation is really crucial, but you have to be able to back up why you're doing that and why you think it's percentages that you have to be worried about instead of actually levels itself. We can skip this one. So those are just some algebraic properties that hold for OLS by construction. That's what we designed our model to be that. So now we can talk about the statistical properties of OLS. So we make a couple assumptions that are not too strong, but sometimes they can be about our model, so we can kind of make statistical inference. So for example, the population regression function is linear in the parameters. So that's by design. We design that and we estimate the model as such. Now, if the true population regression function is not linear, then we are misspecifying the model, and we're going to have all kinds of bias and problems in our data. So this is an assumption we have to make because we're designing the model to look like this. Assumption 2 is we have a random sample of data. For example, if you're running your data on economics grades and some characters about students, and you only took the top 100 students, that's not a random sample. It's a very selected sample, and we don't want that because we want to estimate the population regression function. So you need a random sample and not a selected sample. Assumption 3 is the sample outcomes on X are not all the same. So in math words, there exists two indices. So maybe you can think of 1 and 2. So the first 2 observations where the X's are not the same. So there has to be some sort of variation in the X's. And then for the 0 conditional mean assumption holds. So the expected value of epsilon given X is equal to 0. So again, we're not going to go too much on the math, but you should kind of understand what that means when I say the conditional mean assumption and things like this. So OLS is unbiased. So if it was biased, we would have beta 1 plus some sort of bias parameter. So I'm not going to go through too much of the math, but I'm going to kind of fly through it and hope you kind of see what is happening with some of the conditional mean stuff and why it's an unbiased estimator. But so pretty much we have this from before. We solved for this before, and we can transform it to this to look like this. Using the first assumption we made, we know that the true form, or we're assuming the true form of the data generating process, the true model, looks like this. And then we can rewrite all of this like this, right? Now, if the sum of xi minus x bar equals 0, and the sum of xi minus x bar times xi equals the sum of the squared differences, then we can rewrite the estimated beta 1 as beta 1 plus this guy. And this is our bias parameter. Now, if you remember, we're going to try to figure out a way to get this numerator to equal 0. Because if this equals 0, that means that our whole bias parameter equals 0, which means that it's unbiased, which means the expectation of this equals this. And that's kind of what we want to show. So using the conditional expectation of the last equation, we can do beta 1 hat given x equals this expectation. So that's just going to be beta 1 still, as you see here, times the expectation of this given x. And if we distribute this and kind of rearrange it, we get the xi minus x bar times the expectation of this. And we assume that this equals 0. And if this equals 0, then we're multiplying this whole numerator by 0, which means that we have the expectation of beta 1 hat equals beta 1. And you can do it similarly for beta 0, but it's important to show that that OLS is unbiased. That's very, very important. So all we're gonna be able to say is those 4 assumptions can help OLS be unbiased, or we assume OLS is unbiased at that point. So on average, essentially, if you run this model over and over again, you have different data sets, you can get the right estimates on average. So if one of these assumptions, 1 through 4, does not hold, we're not guaranteed anything. And that's not good, right? So we also don't know anything about how confident we should be in our estimates from the single sample. So now we're gonna have to turn to the variance or the statistical inference properties of OLS. So the variance, we need to figure out the variance of beta 1 and beta 0, but we have to assume something first. We have to first assume something called homoscedasticity, which means that there is some variance greater than 0 where the variance of epsilon given x is this number, this variance term. And this variance term does not depend on x. It is constant throughout. So the variance of your errors should be the same given x, right? And this is pretty easy to find out. You can just apply your errors, your estimated errors given x, and see if this assumption holds. So we can kind of rewrite this as the variance of epsilon has to equal some constant number. It doesn't matter what that number is, it just has to be constant and not vary with x. So heteroscedasticity is the opposite of homoscedasticity, where the error term is not, the variance of the error term is not the same across the x values. So we're gonna create a standard error, and that standard error is going to be accurate for your beta 1 and your beta 0, given that you have this constant, variance of your error terms. If you don't, then you're going to have your standard error is going to be calculated incorrectly. Therefore, you can't make statistical inference. So we'll talk more about homoscedasticity and issues, because there's almost always heteroscedasticity in your models. It's just a fact of life. So here's an example of homoscedasticity, where you see here's the variance of the error term at every x. It's exactly the same, right? Now, an example of heteroscedasticity would be this one, where you have very tight standard deviation, you have a medium standard deviation, and you have a very large standard deviation as x increases. So the standard deviation is related to x. So I'm going to go back one slide. So when to believe in heteroscedasticity. So there's a subtle point where the variance of y given x is equal to the variance of epsilon given x. Because if you remember, if you know what y equals, it's going to be beta 0, which does not vary, it's a constant, plus beta 1x. And again, though beta 1 is a constant, and you're already doing x given x, so that's going to be 0. The variance of x given x is 0. So the last thing you're left with is epsilon given x. So a way to decide, do I have heteroscedasticity in my model, or homoscedasticity rather, either one? Does the variance of y depend on x? So in other words, if I'm looking at housing prices and I'm looking at square footages, is the variance in the square foot of sale price given square footage increasing, decreasing? Is there a relationship between house price variance and square footage? And I would probably venture to say yes. If you have more square footage, you probably have a larger variance because you're bounded at zero, right? At $0. So in this example, you have wage given education, beta 0 plus beta 1 times education. Do we expect the variance of wage given education to be constant? Probably not. Wages are going to vary more for more educated people. So for example, you have education here, right? So as it increases, your variance in your wages can increase, right? Because you can, if you have a lot of schooling, you could be a lawyer, a doctor, or you can be like maybe a PhD in something that's doesn't pay a lot of money, or maybe you have you've been in art school for your whole life for super long, and you're not making a lot of money, right? So there's more of a variance here. Whereas if you don't have a lot of education, maybe you're working a more of a minimum wage job, which is like almost no variance because it's just everyone's making the same amount of money. So we're not going to go over proofs, but the variance of beta 1 and the variance of beta 2 are described by these mathematical expressions. And we're going to have the variances decreasing for both of these in this. So if this is increasing, more variation in x, right? If the sum of this is increasing, which it almost will certainly if I increase n. If this n increases, if I get more and more data, the sum is going to increase more and more. Then these variances are going to decrease because this denominator gets larger. So if we can see more variation in x, we kind of are able to learn a little bit more about the process. We can get more precise estimates. So in practice, we don't know this sigma, so we have to estimate it. So sigma squared, or the variance, is going to equal the variance of the epsilon. So we can use our residuals to estimate the error terms. We can skip the math, but pretty much R or any sort of program is going to give you your standard error estimates. So I'm going to jump up a little bit, and we're going to have standard error of beta 1 is going to be sigma hat, which we estimated over here, sigma hat, right? We can estimate it, divided by the square root of the sum of xi minus x bar squared. So again, we're not going to go through the math very much, but because R is just going to spit this out for you. But this standard error is going to be really, really important because it's going to enable you to make statistical inference about your regression models, which we'll talk about later down the road. We talk about significance and things like that. So as a summary, it's been a pretty long slideshow. Our assumptions lead us to OLS estimates for the simple linear regression model. If these assumptions are violated, we may need to make adjustments, aka we might need to use a different way to calculate standard errors if we have heteroscedasticity, which we'll talk about when we in due time. For right now, we're just going to use the regular OLS estimates for standard errors. The zero conditional mean assumption is quite heroic for the case of a single explanatory variable. Obviously, there's going to be a bunch of things that influence variables, so we need to control for a bunch of them. And in the next chapter, that's what we're going to do. We're going to learn how to use multiple explanatory variables. So instead of just using housing price and square footage, we're going to be able to use, okay, well, now we can use square footage, we can use number of bedrooms, number of bathrooms, and a slew of other things. And then using these 5 assumptions we made about OLS, these estimates have the lowest variance of any possible linear unbiased estimator. So we're going to have the smallest variance estimate that's also unbiased. And those are 2 really, really important things. We want that low variance so we're precise. We want unbiased so we're right. If we were really small variance but biased, it wouldn't really help us because we're really confident that we're biased. That doesn't make sense. And if we have a really high variance unbiased estimator, well, we're not really that precise. So OLS gives us the lowest variance unbiased estimator. And now for the rest of the chapter, the rest of the module, I'm going to do a little bit in R now so we can kind of show, okay, well, we have all this theory, great, it's a lot of math, but let's see it in practice.